All right, in this section, we're going to talk about a special type of motion in which we're confined to move along a circular pathway. Now, if you take a look on the screen here, you'll see a circle. What I mean by this is, let's say we have this red point here, down here at the bottom, and let's say this point can move around, but at all points in time, it's got to be along this outside circular path. Now, normally, if we were doing this and we wanted to define where this point is, we could use a vector to do so, and that vector would have two Cartesian coordinates, x and y. Uh, Basically, this point has 2 degrees of freedom, or 2 variables that we could freely move around to tell you where it is. However, because we are confined to move on a circle, our x and y coordinates are subject to a constraint. And that constraint, realistically speaking, just simply says that if you take x squared and y squared and add them all together, that has to equal to the radius of the circle. In other words, the radius of the circle for these particular sets of points are constrained. Right? So the radius of them has to stay constant. What that means is if we had a vector here in green, right, which represents the position of where we are, it could rotate around, right? But at all times, it has to be on the circular path. Now, when dealing with this bottom equation here is known as a constraint. And if you have 2 degrees of freedom, 2 variables that you can freely adjust, and 1 constraint, what that means is you only need 1 effective variable to represent this particular system. And for this, the easiest choice of single variable that you would have left is an angle theta. So you could, well, that did not turn out well. Hang on. Make this a little bigger. Is an angle theta. So you could define some reference point, put theta in here, and as long as you knew this angle relative to whatever reference points you've chosen, if the radius is constant, you can tell me where you are. This here is typically speaking what we refer to as an angular style coordinate system. It's similar to the angular style coordinate system we were discussing previously. And in this case, it's actually easier than the Cartesian system because we have this constraint that's present. Now, in terms of dealing with this, we do have to set some conventions here. The first convention we set is for the direction. And this is a convention straight from math. It basically says if you're going counterclockwise, this is a positive angle. And if you're going clockwise, this is a negative angle. So this angle that we're going to define is going to be a vector. It has to be a vector because we need to be able to distinguish which way we're going around the circular pathway. But instead of using 2 separate coordinates, we can just use positive and negative. Now, with this being said, it is actually very closely related to the other systems of displacement that we've looked at. So what you'll see showing up on the screen right now is the characteristic equations for dealing with angular motion. Now, in terms of reading these, they actually should look fairly familiar, albeit with different variables. This first one is saying that the final angular velocity is equal to the initial angular velocity plus the angular acceleration times the change in time. And this bottom one here is saying that the angular displacement is equal to the initial angular velocity times the change in time plus 1/2 the angular acceleration times the change in time squared. What you'll notice about these is they should be very familiar. In fact, if you compare them to our regular velocity, displacement, and acceleration equations, you'll notice that they're exactly the same. The only difference is the ones at the top now deal with angular quantities. Now, the reason why this works is because if you're constrained on a circular path, the normal quantity, which are these ones here, are related to the angular quantities through a multiplication by the radius. In other words, if you want to determine, say for example, the normal final velocity, if you're constrained to a circular path, you can do so by taking the radius of the circle and multiplying it by the final angular velocity. Now I've used a w here. The w looking symbols used here are actually the Greek letter omega, but it doesn't really matter much so long as you know what you're talking about. Now, there is a reason why we study the system in general, and that's simply because it shows up a lot, like all the time. And for the life sciences, probably the most striking example of this system is if you're dealing with the limbs of something. That's a lot. And what I mean by that is if you take a look at a person, uh, typically speaking, they have limbs, so we're just going to remove this person's arm, right? Not exactly the best surgery, but and we'll take a look at what happens. So if you extend your arm straight out, your arm, typically speaking, has a finite length and it's attached to your shoulder. If you rotate this around, the radius or length of your arm doesn't change, but the angle that it is, say, relative to the horizontal, can change as you move it back and forth. I'm trying my best to keep the length of it the same. And that's one place in which you will see this system. In general, though, you will see it in pretty much every mechanical system that has a fixed length, rigid object connected to some pivot point. And this system shows up in pretty much every biological system that you can imagine, so long as the things have, like bones and other such things. So that's why we study it in general. It's much easier as well to deal with this in terms of angles than it is to use Cartesian coordinates. So it is a departure from a lot of the other systems that we've looked at.